Hello, welcome to another session on Math for Data Sciences. So, in our previous session, we looked at some of the applications of differential calculus. So, we looked at local maxima, local minima, and inflection point. So, these were the points of extrema which we got using by keeping the first derivative value of the function as equal to 0. So, these are points of extrema. And how we differentiate between the three type of points are we do the second derivative test. We find the second derivative of the function, and if it is less than 0, then the points which we got from y dash equal to 0, x1 and x2, let us say, and if y double dash is less than 0, then it's a point of maxima, and if it is greater than 0, it's a point of minima, and if it is equal to 0, then it is an inflection point, and therefore it is not of much use to find the local maxima or local minima. Just for the sake of completeness, an inflection point is also called a saddle point when we consider these derivatives in higher dimensions. So till now we were only looking at a couple of variables x and y, and therefore we are bounded by two 2D graphs. But when we look at similar kind of problems in higher dimensions and we get the first and second derivative both equal to 0, then the inflection points are also called saddle points. Then we looked at partial derivatives, which is nothing but if we have to find a derivative of a function in more than one variable, and we are finding the derivative with respect to, let us say, x, then we just assume that y is a constant and we find the derivative of df upon dx, which is considering y as constant. So that is how we were able to compute the partial derivatives. Then we looked at mixed partial derivatives, which is nothing but we just do the partial derivative of the function with respect to one variable. So we do it by y in this case, and then whatever function we get from this partial derivative, we do the partial derivative of that function with respect to another variable, so x in this particular case. Then we finally also looked at the chain rule of partial derivatives, which is nothing but when we are finding the partial derivative of a function where both the variables x and y, or even at least one of them, is a function of another variable. So it is possible that x is a function of variable r and s, and y is a function of variable r and s. Then we used chain rule to get the partial derivative of the function f with respect to any one of these two variables, r or s. So we find the partial derivative of f with respect to x, multiply it with del x upon del r, because x is a function of r, and then we add the same thing for y as well. So this is how we use the chain rule to get the partial derivative in this particular case. Now moving ahead, we'll be looking at a very important machine learning application for partial derivatives. So what we'll be looking is we'll try to get, or we'll try to basically derive the best fit line, which is also called the simple linear regression line, for a set of points where the set of points are defined. If you look at this particular graph here, what we are doing is we are plotting height on the x-axis and weight on the y-axis, and the points which are represented here each point here represents a student in a particular class. Now our aim here is to get the best fit line which passes through these points. So it could be this particular line, it could be this line, it could be any of these best fitted line. So the criteria to get the best fitted line, so this is called, let us call this best fit line. To get this, we use the OLS criteria. Now by OLS I mean ordinary least square method. So what we do here is, what is the meaning of OLS? We minimize the sum of error squared for each point. Now, since there are two variables here, x and y, x represents the height, and we are trying to predict weight using x by getting a linear relationship between the two. The best fit line, since it's in the 2D plane, would look like y equal to some constant a plus some constant b into x. Here, a is called the intercept, while b is called the slope of the line. So this is, in general, this is the equation of a straight line on a 2D plane. So this is a general equation of a simple single line on a 2D plane. If we keep changing the values of a and b here, we keep getting different lines as shown here. Now we have to get the values of a and b such that we are able to minimize the sum of the error square for each point. Now what is error in this case? So let us look at this particular graph here. Now let us say this purple line here is the best fit line. So let us assume right now that this is the best fit line. Now let's pick up any one point. So there were many points here. Let us just look at it from one point perspective. So let us say that point is x, and the actual value with respect to x is y. For this particular student, we have x as the height and y is the weight. Now, since the best predicted line is the purple one, if we find the value of y for this particular value of x, we get the value as y hat. So this is the predicted value for height x. Okay, so y hat represents the predicted value of x, while y represents the actual weight value for the student. Therefore, what would be the error? Error is computed as observed value minus predicted value. So this is called forecasting error, and this can be written as y minus y hat. Since y is the observed value, that is the actual value, and y hat is the predicted value. Now, one thing to note, I have written here as EI. So what does I represent? I is nothing but the student I. So first, since we are selecting one student here out of, let us say we have total n students, and xi, yi represents matrix for student I. So xi is the height of student I, and yi is the weight of student I. Similarly, y hat I is predicted weight for student I. So these are the notations for different metrics which we are going to use here. Now, since we have to minimize the sum of error square for each point, what we do, so let us say now we already have error defined as observed value minus actual value. So let us keep it in terms of I. Now, since we have n students, and based on our OLS definition, we are minimizing. So minimize sum of error square. This is the error term which we are trying to minimize here, or you can even call it a loss function in this case. And we have to minimize this particular function now. So let us call it capital E here. Okay. Now, if we have to calculate capital E, we can write it as summation of yi minus yi whole square. Now we are summing up the error terms for each of the n points which we have. So this goes from I equal to 1 to n. Now, since we already know y hat predicted value, so y hat predicted value is calculated using the best fit line. So as you can see, this best fit line, the purple line on the right graph, was used to get the predicted value for corresponding to the height x. Therefore, we can write the predicted value here as a plus bxi, since this is the best fit line equation that we had assumed earlier. So note that we still don't know a and b, which is our aim here. These are the parameters which we need to find as the best fit line. Once we get that, we'll get the equation for the best fit line as a plus bx. Now we basically, so in error term now, we can replace yi hat by a plus bxi minus yi whole square. Now, since we have to minimize this, now it is when we can use our knowledge for partial derivatives. So what we do is, we have two hyperparameters or two parameters here. We find the partial derivative of this error term with respect to each one of these parameters. So let us first do that. Del E upon del A is summation n I equal to 1. So we use the substitution rule or the chain rule of differential calculus, and what we do is we assume u is equal to a plus bxi plus yi, and therefore we have summation of u square. Now the derivative of u square is 2u, so we can write it as 2a plus bxi minus yi whole square, and the derivative of del u upon del a is 1. Therefore we are only left with this particular term. There is no 2 here, since the derivative of u square is 2u, and we equate this to 0. So if you remember the first derivative test, to get the critical value, we equate the first derivative as equal to 0. Now 2 is a constant. Since the RHS is 0, we can simply remove 2 here, and we are left with a plus bxi minus yi is equal to 0. Now just separating out the summation terms, since a is a constant, if we are summing up n times a, we would be getting na, plus we can bring out the constant b, and we still have the summation xi minus summation yi. This is equal to 0. Now we can write the value of a here as, so a could be written as summation yi minus b summation xi upon a. So this is the value of a in terms of b. Now what we do, we find the second partial derivative, that is del e upon del b is equal to 0, and we have del e upon del b completed here as, so once again we use the chain rule of differential calculus. We will be left with summation of, again, 2 a plus bxi minus yi. Now the derivative of a plus bxi minus yi with respect to b is xi. Therefore we have an xi here as well inside the summation, because derivative of bxi with respect to b is xi. So if we are using the chain rule, we need to multiply it by del u by del b, which is xi. Now this is again equated to 0. We can cancel out 2. Therefore we are left with a summation of xi plus b summation of xi square, since there is an xi here and xi outside, and then minus summation of xi yi equal to 0. Now we can put the value of a from this particular equation, the first equation which we got, into this equation to find the value of b. So once we do that, we have summation of yi minus b summation of xi whole upon n summation of xi plus b summation of xi square minus summation of xi yi equal to 0. Now we can multiply the whole equation by n, and we are left with summation xi summation yi minus b summation of xi whole square plus nb summation of xi square minus n summation xi yi equal to 0. Now we can bring b on one side and find the value of b. So b n summation xi square minus summation xi whole square. So we use these two terms, and then the remaining one are on the other side, n summation xi summation yi minus this is xi yi minus summation xi summation yi. So we get the value of b now as n summation xi yi minus summation xi summation yi whole divided by n summation xi square minus summation xi whole square. So this is the formula to get the value of the slope coefficient. Now just to explain what these summation represent here is, summation xi is basically nothing but sum of heights of all students. Similarly, summation yi is sum of all weights. N is the number of students for which the analysis is being done here. So this is how now we can put all the values here and we can get the required result to get the slope of the equation. So once we have got the value of b, the value of a is very easy since we already have a relation between a and b. So a is computed now as, we can pick it from here, sigma summation yi minus b is already known now, b summation xi whole upon n. So we can use these two formulas to get the required value of the slope and the intercept. And once we have done that, the best fit line equation, or the equation for best fit line based on OLS ordinary least square method is given as a plus bx equal to 0, equal to y. So y equal to a plus bx is the required final best fit line, which is also called the simple linear regression line. So this whole process or algorithm is called simple linear regression. So this is how we can use the partial derivatives and equate them to 0 to get the critical points to minimize the loss, total loss function. And loss function in this case is defined as the sum of the square of all errors for the endpoints. And this is how we can get the required intercept a and slope b to get the best fit line. So this is one of the applications of partial derivatives directly shown in a machine learning algorithm.